The following is a review of the quantitative methods principles designed to address the learning outcome statements set forth by the CFA Institute. It is also covered in statistical concepts and market returns. The first LOS is to distinguish between descriptive statistics and inferential statistics, between a population and a sample, and among the types of measurement scales. Descriptive statistics are used to summarize the important characteristics of large data sets. The average value and measures of dispersion are common descriptive statistics. Inferential statistics concerns the procedures used to make forecasts, estimates, or judgments about a large set of data based on the statistical characteristics of samples of data from the larger set. Statistical inference is based on probability theory, and we will get to that, but in this section we will be concerned with descriptive statistics. Different statistical methods use different levels of measurement or measurement scales, which can be classified into one of four major categories. Nominal scales are the level of measurement that contains the least information. Observations with nominal scales are classified or counted with no particular order. An example of the use of a nominal scale would be to make observations on bonds and assign a number 1 to a municipal bond and a number 2 to a corporate bond, and so on for each type of bond. Another type of measurement scale is an ordinal scale. An ordinal scale represents a higher level of measurement than a nominal scale. When working with ordinal scales, each observation is assigned to one of several categories. Then these categories are ordered with respect to a specific characteristic. For example, the ranking of 1,000 small-cap growth stocks by performance may be done by assigning a number 1 to the 100 best-performing stocks, the number 2 to the next 100 best-performing stocks, and so on through the assignment of number 10 to the 100 worst-performing stocks. Based on this type of measurement, it can be concluded that a stock ranked 3 is a better performer than a stock ranked 4. But the scale reveals nothing about the performance differences or whether the difference between a 3 and a 4 is the same as the difference between a 5 and a 6. A third type of scale is an interval scale. An interval measurement scale provides relative ranking, like ordinal scales, plus the assurance that differences between scale values are equal. Temperature measure in degrees is a prime example. Certainly 49 degrees centigrade is hotter than 32 degrees centigrade, and the temperature difference between 49 degrees centigrade and 32 degrees centigrade is the same as the difference between 67 degrees centigrade and 50 degrees centigrade. The weakness of an interval scale is that a measurement of 0 does not necessarily indicate the total absence of what we are measuring. This means that interval-based ratios are meaningless. For example, 30 degrees is not 3 times as hot as 10 degrees. The last type of measurement scale that we're going to discuss is a ratio scale. Ratio scales represent the most refined level of measurement. Ratio scales not only provide ranking in equal differences between scale values, they also have a true 0 point at the origin. The measurement of money is a good example. If you have $0, you have no purchasing power. But if you have $4, you have twice as much purchasing power as you would if you had $2. Our next learning objective is to explain a parameter, a sample statistic, and a frequency distribution. A population is defined as the set of all possible members of a stated group. A cross-section of all the stocks traded on the New York Stock Exchange is an example of a population. A measure used to describe a characteristic of a population is referred to as a population parameter. While many population parameters exist, investment analysts are primarily interested in just a few, specifically the mean return and the standard deviation of returns. Frequently it is too costly or time-consuming to obtain measurements for every member of a population, even if it is possible. In this case, a sample may be used. A sample is defined as a subset of a population. Once a population has been defined, a sample can be drawn from the population, and the sample's characteristics can be used to describe the population as a whole. For example, a sample of 30 stocks may be selected from among all stocks listed on the New York Stock Exchange to represent the population of all New York Stock Exchange traded stocks. In the same manner that a parameter may be used to describe a characteristic of a population, a sample statistic is used to describe a characteristic of a sample, such as its mean or dispersion around the mean. A frequency distribution is defined as tabular presentation of statistical data that aids the analysis of large data sets. A frequency distribution summarizes statistical data by assigning it to specified groups or intervals. Also, the data employed with the frequency distribution may be measured using any type of measurement scale. Keep in mind that a frequency distribution is constructed by assigning data to specific intervals or groups. To construct a frequency distribution, the first step is to define the interval to which observations will be assigned. The range of values for each interval must have a lower and upper limit, and be all-inclusive and non-overlapping. Intervals must be mutually exclusive so that each observation can be placed in only one interval, and the total set of intervals should cover the total range of values for the entire population. Once the intervals have been selected, the observations must be assigned to their appropriate intervals by counting the observations that fall within each interval. The absolute frequency, or simply the frequency, is the actual number of observations that fall within a given interval. Let's assume that we have 20 years' worth of annual returns for a given stock, and we want to construct a frequency distribution. Let's separate our data into 10% return intervals. Having defined our intervals, we assigned a number of annual returns that fall within each given interval, and then count the number of returns within each given interval. So let's assume that 7 of the annual returns out of 20 fell within the 0 to 10% interval. This means that the absolute frequency is 7 for the 0 to 10% interval. The next LOS requires us to calculate and interpret relative frequencies and cumulative relative frequencies given a frequency distribution. Next, let's explain relative frequency and cumulative relative frequency distributions. Relative frequency is calculated by dividing the absolute frequency of each return interval by the total number of observations. In other words, relative frequency is the percentage of total observations falling within each interval. Continuing with the example we just described, and recalling that we had 7 return observations that fell within the 0 to 10% interval, and that we had 20 total observations, the relative frequency in the 0 to 10% interval is 7 divided by 20, or 35%. The cumulative relative frequency for any given interval is the sum of the relative frequencies up to and including the given interval. This is the percentage of the values that are in or below the given interval. Our next LOS asks us to describe the properties of a data set presented as a histogram or a frequency polygon. A histogram is the graphical presentation of the absolute frequency distribution. A histogram is simply a bar chart of continuous data that has been classified into a frequency distribution. The attractive feature of a histogram is that it allows us to make a quick visual observation of where most observations are concentrated. To construct a histogram, the intervals are scaled on the horizontal axis and the absolute frequencies are scaled on the vertical axis. To construct a frequency polygon, the midpoint of each interval is plotted on the horizontal axis and the absolute frequency for that interval on the vertical axis. Each point is then connected with a straight line.